Okay, so good morning to everybody. Welcome to this morning session and to the first lecture of David DiVincenzo on quantum electrical circuit.
Okay, thank you. So I begin my tutorial lessons. So I'll be giving you a lesson today for the hour and a half in the morning, and a lesson 2 days from now. So that sounds at some level like a long time, but what I'll be teaching you is the contents of this book that we have. Sorry, I've cut off some of the authors because I wanted to emphasize the picture in the middle, but this is the front cover of our book, Lecture Notes on Quantum Electrical Circuits by Alessandro Chiani, myself, David DiVincenzo, and Barbara Terhal. And while 3 hours is a long time to lecture, we usually do this as an entire master's course. So some streamlining, condensation will be needed. So of course, I'll be just mainly touching on giving you the high points and what I think would be of interest here. This, of course, is not so directly on the line of quantum trajectories. You know, this is not exclusively a discussion about quantum measurement, but the point of the work I'll be describing to you is to have a full description of a device like this. So, with all of its complexity, but nevertheless seems to work in some settings and is taking us on the path towards quantum computers, but maybe other devices as well. I hope tomorrow I'll get back to an explanation within this setting of my whole story of how you measure my ultra compressed photonic modes that are flying along on a transmission line. So transmission lines are a pretty big part of this story, but let's see, I don't remember exactly which chip this is. This is a chip from Delft, surely, but maybe I'll do it with reference to the next picture. This is a chip that is built at the ETH in Zurich. And to take you through the elements that need to be described, and I will assure you that in the end we have a very high accuracy description. We have sort of as accurate as you wish of the relevant dynamics of this circuit, to the extent that we recently considered what I would say is sort of a 5% effect, and we're able to very accurately and confidently measure this new 5% effect within this circuit theory. So this is a circuit, as it happens, with 17 qubits, and they're very easy to spot because they're in this fragment of a square lattice, and the qubit is here, and I zoom way in, and the qubit is sort of there. It's a very tiny little thing, or at least the key element of the qubit is a very, very tiny, minute thing, not 1 pixel on this picture, which is the Josephson junction. So we'll have to incorporate our understanding of Josephson junctions. But there are not many Josephson junctions. There's one, or actually there are 2 Josephson junctions for each of these 17 qubits. So there are 34 Josephson junctions, and then a whole lot of other stuff. And if I were giving a talk about this is not my work, but I would be telling you about qubit couplers. Well, I would first back up and say some of these are ancilla qubits and some of them are data qubits, and they're used to achieve an error correction experiment. And there are couplers between the qubits that actuate 2 qubit gates that enable entanglement. There are tuning elements that change locally magnetic fields, that change the characteristics of the qubit. There are measurement resonators, so-called. There are filters, so-called Purcell filters, and there are readout lines, and they're all color-coded for that description. But I won't say so much about that. But my main objective in the coming minutes is to say how we write down a Hamiltonian of this. As I say, sort of from first principles, not first principles in the way that the materials people mean it, but based on a full description, as complete as you wish, of the dynamics of this structure in such a way that we get in the end, highly accurate Hamiltonian, with which we can do a variety of things. We can indeed model the action of gates. We can model the action of measurements. But I wanted to first, set up how we think about this. So I plunge immediately into chapter 5, actually, of our book, and I'll circle back and get to the beginning of the book afterwards. But chapter 5 says that you should, or a good way to approach this is to first recognize that most of what's going on here is electromagnetics. That is, you send electromagnetic signals into this device. They enter via these transmission lines, and they reach some point, and then they do something. And so these many, many contacts, or the edges, are the places where these signals come in or out from the outside world. And then all of this is described by some electromagnetic, dynamics. And in fact, almost all of it can be described with linear dynamics, and that's what I'll write. My first few equations will be emphasizing that point. The big exception being the Josephson junctions. Now, the Josephson junctions, if you look, deep inside at this sub-micrometer level, I'm going to use a space that I wouldn't otherwise use. So there's some, at the sub-micrometer level, there's some metal, and it comes in, and then there's some other metal, and it's in contact, but only through an oxide junction. And the dynamics of this little region is special. Must be considered differently. It is not governed by the laws of linear electrodynamics, but everything else is. So the first step in this analysis to isolate out and have as compact, as clean a description as possible of the linear part of this problem. So that's what I'll launch into. I wanted to also emphasize something that, also make it a slight quiz, just to again orient myself. I learned yesterday that you're all theorists, so that's fine. That's very good. But now I want to see how many of you are electrical theorists, and that will be a sort of distinguishing feature. So you see all these beautifully colored lines, and you can easily think, oh, they're wires. And they kind of look that way in the coloring. But in fact, they're not, in the following sense, that there's, are any of these yellow? No, it doesn't matter so much. Well, okay, there's some pink ones. So what you see in this schematic is a pink lines in various places, here. And that's clearly, something that's going to carry signals. But it's not just a wire. It is a wire. It's an electrical wire, probably made of aluminum in this case, maybe niobium, one of those two. And it's resting on a dielectric, a very high quality dielectric. And then there's actually a gap. And then after a short distance on both sides, there's more metal. And so in this, and the metal then is very wide. It's a thin film of metal. And it just goes on for a long distance. So somehow when you zoom out, well, when you choose this coloring, it should be by this scheme that all of these have a sort of deep color. It's all mostly a sheet of metal with just these little gaps running along the sides, the top and bottom of these wires, these center conductors. And that forms a transmission line. So that's one aspect of what needs to be described, is that these are actually transmission lines. They're usually, the quiz is coming up. They're usually 50 ohm transmission lines. And I just want to check, is this often, it's interesting to separate who knows what here. Do you know why it's 50 ohms and not, 3 milliohms? What is the distinguishing point about the physics of these things that makes it natural for it to be 50 ohms? Anybody? Professors? You could raise your hand, I'm sure. But, okay, so no. All right, interesting. So, the clue is that it's both an engineering and a fundamental number. It's fundamental in the sense that it's very close to 377 ohms, which is so approximately equal to 377 ohms. Okay, I'll pause again. You theorists, do you know what the significance of 377 ohms is in our world? No? Okay. Well, if you cast your mind back to your E&M studies, it should have been in there, and you maybe passed an exam where you had to know it at some moment. This is equal to the square root of mu 0 over epsilon 0. So it's the so-called impedance of free space, impedance of the vacuum. So it's an important physical quantity. And now 50 ohms is not 377 ohms. However, it's sort of a good engineering approximation to it. It had to be standardized. And in fact, it's relatively straightforward geometrically to make a device. I mean, you have certain geometrical parameters, the width of this, the width of the gap. That's about it. And you know, for a wide range of parameters, it's in this neighborhood of this fundamental constant that sets the scale of it. And but engineering standardization says you should make it some number that everybody agrees on. So 50 ohms is one of the several. There's 75 ohms. There's 100 ohms sometimes. Back when I was young, there would always be a connector in the back of your TV or something, and it would say 50 ohms, and it would say, you know, it would be the place where you'd plug in your transmission cable. I think they're still back there, but so you should have a look at the back of your televisions. Okay, now that will actually come up. That is, there will be an analogous ratio, square root of a ratio that will come up before the end of today that will be relevant, in fact, for the second quantization of some of our circuits. So, so it even, you know, mixes into some of the more fundamental physics. Okay, now, I promised that I would set the stage here, and I'll do it by announcing this sort of black box paradigm. That is that, and the schematic of this is the following, that we have what are called ports. Now, many ports, and then a, quote, black box. Now, in this picture, we have really a lot of ports. This would be quite an ambitious exercise to compute, you know, to follow the program I'm describing for this, because, you know, each of these things is a connector to the outside world. It's a place where this transmission line connects to the outside world. But I'm going to, what a port means is it's a pair of conductors. It's a place where you can put your probe, like here and here. I don't know if you can see that, there and there. So the center conductor and the ground. Maybe I'll write these. Center conductor, and then ground, which is both on the top and the bottom, ground of the center conductor. And they're electrically separate, but I can connect something to it, like a signal generator or something like that, something from the outside world. And so that's what's schematized here. So there's here's a pair, here's another pair. Now I'm going to announce yet a different kind of pair. When I go deep inside these qubits and I encounter this element, this Josephson junction, I say I want to treat that separately. And so the way I'm going to do that is I set another pair of terminals. Here's a point and here's a point, just nanometers apart or a few hundred nanometers apart. And I'll call that pair the port. I don't know if I said that word yet. So this is a port. So, and that's where they are physically. Now we're going to deal with then the entire, quote, interior, but it looks like sort of the exterior with respect to this Josephson junction here. This will all be a linear electromagnetic problem. So it's our job to do the dynamics of that. For a long time, we'll be doing classical physics, that is, or classical electrical engineering, you might say. So for a long time, the job is to set up the dynamics to recognize that it is describable as a lossless system, mechanical system, in the sense of not quantum mechanics, but classical mechanics, and then to quantize it after you've got all that sorted out. So there's a port. So there are ports all along here. And again, in many languages, it's called two poles, Zweipol or something in German, just to emphasize that it involves, you know, a pair of contacts, so to speak. So here, 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 and then all 17 of these Josephson junctions get their own assignment as a port, and then the rest is, okay, so the rest is a linear time invariant. I'll say network. Now, network implies something kind of discrete, but you see this, maybe you shouldn't take a discrete view of this. This is just various metals in various shapes. Sometimes the metal crosses above another metal, so it's not even entirely two-dimensional. So, but we will sort of impose a network view on it. We will impose a more discrete view on it than what is, available here. Yes.
The Josephson junctions are inside the qubits.
Yeah. Yeah.
And what's the scale of this?
Oh, good point. Scale is a couple of centimeters or something like that. So yeah, very good point. This is a rather large chip. So, that big, whereas the Josephson junctions are 100 nanometers. So, this working area is extremely tiny. So it's negligible on the scale, but it has an enormous effect on the dynamics, nevertheless.
This is a metal and these are kind of etched on that. The channels are kind of waveguides?
Almost everything are waveguides in this picture. Let's see if there are any exceptions at all. This stuff interior to the qubit is not entirely just waveguides. There's other shapes of metal. These sort of star-shaped things are, again, the sort of plate of metal of the shape of this star. And that will affect details in the sense that it affects the electromagnetics, although not that deeply. Okay, now, yes?
Just and the little bar which are orthogonal to the line correspond to capacitors.
You mean like here?
No.
Oh.
On the line, you have a little bar with capacitors.
Okay, I have a solution for you here. Point to the screen so I know what you're referring to. By the way, we're violating the microphone rule. Right there. Yes, very good. Yes, indeed they are. So you know a lot about these things. If you zoomed in on them, they're so-called interdigitated capacitors, but they're places where the transmission lines are interrupted. So indeed, that's an aspect of the electrodynamics. What that will do, okay, aside, so you have a long transmission line. It's carrying radiation, of course. It's surrounded by these ground planes. If you interrupt the center conductor, and that's what's done here, but with various additional features here which affect the capacitance of these two connections, the intervening part is a nice resonator. So it's the Harosh resonator kind of thing. So yes, depending on the boundary conditions, you can short one end. You can short both ends. That gives you different two standard boundary conditions, the Dirichlet-Neumann kind of boundary conditions. So they're all available in this toolkit, and they're all, many of them are in use. These are very purpose-built to do various things. To minimize noise, for example, to make single-shot measurements possible, and that's largely this pair of things is sort of the quote technology of that, and the specifics of the couplings here and here so forth are definitely for that purpose. Now, I coming in don't have to do all that hard thinking. That was done by the experimentalists. I'm now sort of the analyst. I come in and say, well, what have they done? And a way to deal with that is to take advantage of the fact that this is a linear time invariant, actually nearly lossless network. I didn't say that so much, but it's important that these are, although not absolutely crucial, but most of the metals in this device are superconducting, so they have very low loss, not zero loss, because these are all, these are not DC experiments, these are dynamical experiments. Okay, now, the way we discuss this, so both theory, but also if you simulate, so you can make, there are tremendously sophisticated packages for doing the electrodynamics of such a structure. When you feed in a geometrical model, you say where the conductors are and where the ports are, and you say simulate. Now, what does it simulate? Okay, it will, let me go to something here so I can read off a few things. So it will often, or what you will often do as a sort of test experiment, but it's often a numerical experiment, but you can imagine doing it in a testing lab as well. But it's where you temporarily turn off quantum mechanics, you might say. So you feed into here a current, I of t current. So some waveform of current. The rules of the port is that whenever a current goes in one port, it goes out the other. So that's just one of the rules of what makes a port. So you put in an I in some port, and then you ask what voltages are produced. You don't care for this characterization what voltages are produced in the interior. You only care what are the voltages at these ports. So you put this into port alpha, let's say, and then it produces voltages at ports beta. And the equation that will get us started on this, I better be writing it larger than I'm beginning to write it, is that, so this is a linear problem. The voltages should be related to the currents by an integration which involves a linear kernel. So I have an I alpha here of, let's call it tau, I think. Tau, yeah. And I have well, in this case, a matrix kernel, that is, currents at port alpha can produce voltages at other ports or their own port as well. So I have a kernel, which I'll call Z beta alpha, T minus tau. The T minus tau is reflecting the time invariance of this network. And well, it's, as you've seen, set up to be linear. And so I will put my integration from minus infinity to infinity. But of course, I'll already, correct that. Causality will say that voltages can't start appearing until currents have appeared. And that makes this impedance function one-sided in time. In other words, this z of t is 0 if t is less than 0, if for negative time. So it's a function that turns on, so it has this usual causal structure. Now this is the impedance matrix in time. Usually the electrical theorists will take advantage of this time invariance by going to frequency space, or actually more commonly to Laplace space. So let's consider that. So first we have a Laplace transform. So if I have any function of time, f of t, I will introduce its Laplace transform, e to the minus st integral over time. And that produces a function in the Laplace domain S, so Laplace variable S. And because of this linear and time invariant nature of this, this formula gets transformed to a very simple algebraic sort of matrix theoretic formula, V equals Z I, Ohm's law, in other words. Let's see, what do I want to say? I've now suppressed the indices, but I'll maybe underline these to emphasize that you can consider these as vectors, vectors of currents and voltages at the different ports. And then this is a matrix with the dimension of the number of ports. Okay, now it turns out that these conditions, linear, time invariant, but also the condition passive. And that means that there's nothing inside this network that will be delivering energy. There are no voltage sources or current sources in this picture. That can be said somewhat more formally. That turns out to tremendously constrain the form that's allowed for Z of S. So from the point of view of analytic function theory, there's only a very tiny class of functions that are permitted, no matter what is happening, no matter what the details are, whether this capacitor is big or small or whatever. And we're going to use this to jump to a very much more minimal model of this with small numbers of parameters. And so that will indeed be the launching point for being able to describe these. But never, these small parameters, which if I did this lecture from chapter 1, you would just say, well, introduce some arbitrary parameters for these small circuits. But the point of discussing it this way is that these parameters can be known. Because you say simulate this network. This is a pretty ambitious one, I must say, and we'll shrink down to a few ports for further discussion. But it's only a matter of sort of long runs of the electromagnetic software to get the entire function Z of S for the relevant parameters of it, because the theorem is, yes, a question. Now you want to obey the microphone rule.
So, I mean, at least you have some nonlinear element, right? The Josephson junction. So how come you still get like a complete linear response? I mean...
Yeah, because I'm going to, when I complete the description, I'm going to now put Josephson junctions here. So, I haven't said anything about two terminal elements, but in this description, I sort of turn it inside out. And when there's a port, there will be, in this example, 17 ports that are there because they're going to describe the fact that, yes, I'm about to put a nonlinear element here. And in this picture, they will go on the outside. I need a picture with, I don't know, 50 ports or something to describe this Zurich experiment. And about 17 of them will be there to describe what's happening inside each qubit.
Sorry, so where are the ports here? I mean, I thought the ports are at the boundary.
Well, there are two kinds of ports. These are one variety of port,
Right, yeah.
and they will appear here because, so when I complete my description, I'll do things like put a signal. I'm trying to draw the symbol for an AC signal generator here. So this black box by itself is not yet the full description, but it will contain everything I need to know about the linear parts of this structure.
So this is just part of this, this represents some part out here. Is it like a small, how is this related to this?
Okay, so unfortunately I could say this is port 1. I'm going to number them, port 1, and I come over here and there's port 1. And I get to further down the list, I have to number about 30 of them to number all of those. And then I get to a port number 31. And that one will be, let's say, qubit D5 or D9, just because I can point to it. And then I have about 17 of those. Now, I said that there would be more Josephson junctions. It turns out in many cases, what I will terminate this is not one Josephson junction, but 2 in parallel. But that's about it. It's a variety of things that will happen there. And then once you've discussed the terminations, then you have a full circuit, you have a closed Hamiltonian, and you can follow rules, which I'll be reviewing, and get to an answer. Now, sometimes, or in fact, it's always the case, that these external ports, so they're sort of external and internal ports, the software calls them wave ports and discrete ports. But I don't think any of you are busy looking up the GitHub where this software is shown. Normally, or inevitably, there is actually a resistor here. We've carefully banished resistance from the interior of this object, but it's not the case that it's gone. It's somewhere out here. That is the nature of signal generators, or the nature of way signals are introduced into these, is such that there are also resistors. So this is not a lossless I didn't say it here, but I should have also said lossless as a premise. Now, we may indeed want to discuss these resistors, and in fact, this will take us over to the kind of equations that are coming up in Pierre Rochon's lectures, because then a reasonable treatment of these resistors will lead us to master equations rather than to Schrödinger equations. That's a rather long, far down the road for where I am right now. So, but just to set the stage, that would be a fairly complete description. You know, I don't, of course, I don't describe everything. I don't describe all of the, you know, details of what's happening once the wires come off the chip. At some point, I just declare, okay, that's as far out into the environment as I need to go. But it will be possible to write a full quantum description of this entire object. Okay, good. Now I'm getting to Foster's theorem. So now Foster's theorem is something I have written down here, and I just want to get it pretty much right. So let's see. But where is it exactly? Oh, yes, page 89. I'm very grateful for questions, and I'd be totally happy to answer more of them. Right, now here's a good equation. So it was learned in the scalar version of this, that is, if you just have one port, this is a theorem of Foster, 1924. And it says that under the conditions I've stated, Z of S must have the following form. It has, although it turns out to be easier to show it sort of graphically, which I will do in a moment. So it has a sum over poles. Sorry, well, no, we haven't. Okay, this is poles really in the complex function sense. And then some constant, I need a sum m equals 1 to some number of poles. I'll have a little discussion about this number of poles in a moment. There's some uninteresting constant, actually, I'll just make it this way. So there's some constant, has some dimensions, but it is pole dependent. This is basically a residue. And then a pole pair. So we have 1 over S plus I omega m, and then its partner on the other side of the complex plane, omega m, that's it. So that's everything that can go on here, no matter what. And all the complicated things, you know, what's the capacitance and how big is this resonator and what's it doing there, are all captured by these parameters, a pair of parameters, residue and pole position, for a bunch of poles. Now, this maybe wouldn't be so useful if m is 10 to the 23 or something like that, but that's not how it works out. That the number of poles is sort of, well, determined by geometric scales. It sort of involves the following, that the first pole in frequency will be more or less the frequency corresponding to one wavelength of the object in question. Now, that would, we usually go for a much more minimal model than that, I have to say. And in fact, the experimentalists work pretty hard not to have so-called box modes. So box modes are things where indeed you have, where this whole thing acts as a cavity, and there is in fact an electromagnetic mode of that wavelength. They work pretty hard that the first poles that really have any weight, you know, have any residue, are already a lot smaller than that. So one should think that this m, the number of poles, is sort of few, or it's a few per qubit anyway. So yes.
Yes, I have a question about the lambda m, the coefficient. It's a metric?
Okay, I should have said this for the scalar case, although indeed the vector case has an extremely trivial replacement. This turns into a rank 1 matrix. rank 1 symmetric matrix. And no other change. So, I mean, I could have said that right away, but it's just that this was 1924, and this took surprisingly long to sort out, in the sense that even the sources that I really love were quite indistinct about the rank. And one has to think it through for oneself, in fact, to be clear that rank 1 is the right answer. It can be, well, a few points. These are simple poles, so there are no multiple poles. They can, however, sit arbitrarily close to each other, and that somewhat confused people. They say, well, this then could be a higher rank, but that's a kind of accident that they sit, basically on top of each other. It's basically you would need a lot of special symmetry for these to sit, a bunch of simple poles, but sitting right on top of each other, so that this becomes higher rank. And that is indeed, a small addition or thing that we've corrected in this book that maybe wasn't so clear to some of our predecessors. I thought I'd begin showing some of the sources. No, that we're not getting to. Some of the things I'm saying are in this beautiful book, which is pure electrical engineering, but it was used to educate decades of students in the theory of electric networks at MIT by this professor, Ernst Gilliman. And I just throw in here for amusement that he was a colleague of Wiener, whose work you'll be hearing a lot about tomorrow or the next time. A truly versatile theorist, and they're standing here talking about some response function theory, clearly. So Wiener, I mean, this is definitely the more famous name, but these were both faculty members at MIT. And I've seen it stated that that Gilliman was sort of an impedance match between Wiener and the rest of MIT, that he was not otherwise a fantastic match. Apparently this was totally characteristic, that he was always smeared with chalk dust and was carrying a cigar around regularly. So, okay, that's, well, a small aside, but this book will only tell you about Foster's theorem, the original version. And this, there's another book that I love, but which this one. So by this gentleman, who's still alive, actually, Robert Newcomb, even though his book was written in 1966. Linear multiport synthesis. This is a multiport. And synthesis means the act of, writing these things down and recognizing what they mean for discrete models. Don't worry about these words at the moment, but this book is indistinct on exactly this point, it turns out. This is a picture where I tried to express the idea that even though they're ports, they're sometimes, deep inside the electrical structure. Okay, now, usually you see Foster's theorem in a sort of pictorial form, and that will very quickly get me, I mean, you'll be surprised, I've been wandering here and there, but soon I'm going to get to one transmon and one resonator. So we'll spend a long time discussing that. So what does this, expression mean if you write it out? It's a simple arithmetic sum, and it means that it expresses things where there are a set of impedances in series. So impedances sum in series. So you have a Z1, a Z2, ... Zm, and that's the sort of pictorial content of this. But it's much more than that. Each of these is a simple pole pair, and the circuit which gives you a simple pole pair is this: an inductor and a capacitor. So there's an inductor and a capacitor for port 1 and pole 1, pole 2, etc. There can also be, and these are highly important, there can also be a degenerate pole, so we say a pole at 0, at S equals 0, and that's a pure capacitor. And then there's also so this is a pole at 0. This is a pole at infinity, and then these are the finite frequency poles, and then ... And that says that if you were only concerned with one port, and I've given you a whole story for why we intrinsically care about the multi-port case, then this is a universal circuit. For whatever complex electromagnetic things with dielectrics and three-dimensional metal structures and anything you want, they're all universally describable this way. Now that's very handy because we can then we don't have to work on the field quantization of complex structures with very complex matter and dielectrics and things. We can work on the quantization of these guys, and that's of course a much simpler job. That's just a discrete problem. It's a problem of quantum mechanics, not a problem of quantum fields. Okay, so having gotten this far, I think now is the moment to sort of jump back to chapter 1. Except maybe I'll say that, so to complete the idea of, suppose you were just trying to describe one qubit and what it sees in its neighborhood. So indeed, we are going to say we somehow block off or don't even bother with these ports. We just say they're open circuits or something like that. And we have deep inside here one qubit. And this says that from the point of view of that qubit, this is a good description. And so to complete the circuit, we draw this one element. And I will define it if you don't know what it means. Well, okay, aside, you're all theorists, you're all aspiring quantum scientists. How many of you know already the characteristic of a Josephson junction? Now, how many of you know what I mean when I draw this picture? Okay, now we get some hands, but not too many. Okay, well, yeah, Alice and Bob, you should know what it is. Okay, but I'll define it for you. And in fact, I'll spend some time defining what inductors and capacitors are also. Maybe you think you know what they are, but it's good to know, a little bit more concretely what they are. Now, let me just say, this is the quote general circuit. Now, it turns out that on purpose, we often design the environment of the qubit so that there's one resonator whose frequency is sort of in the right band, and I'll have to say what that means in a moment, so that we begin with a much more minimal network. Let me put it here. So minimal one qubit network. So we have, this nonlinear element, and we have this given by Foster's theorem, and that, and we just stop. So this is a one-pole approximation, or really, you might say three-pole, because there's a pole at the origin, and then this gives a pole pair in this Z function. So that's almost the circuit we spend a huge amount of time analyzing. There's a related non-minimal circuit, non-Foster circuit, which has this look, which only differs in how you organize the capacitance part of the network. And I can just say that these are equivalent in the sense that if you choose parameter values for these capacitances, that they, because of Foster's theorem, they're always representable in this more minimal form. And then why do you bother using this non-minimal form? Well, then it becomes more an issue of the physics that in this representation, this middle capacitor, because of the physics of the devices you're making, is much smaller than this capacitance, which you would call, say, the transmon part of the device. And then this is a resonator used for various purposes like the ones we saw yesterday. I mean, there are many invaluable things you do with a resonator coupled to a qubit, and we will be able to discuss a kind of frequency of this nonlinear structure and the frequency of this linear structure, and then a weak coupling between them. So that sets up sort of this minimal scenario, in fact, for which permits you to do many experiments on single qubits. But again, remember the story is that this formalism is far more flexible than this. That is, it can tell you what network you will use for the 17 qubit structure. But now let me, in a sense, pause, or I'm sort of halfway through today's lecture, because I want to now, for the benefit of those of you who are not electrical scientists or who have not seen capacitors and inductors since high school, that we'll sort of review what these are. And in the context of, say, this circuit, we'll say why this circuit has a Hamiltonian, how I can derive it. Now, for that, as I said, I want to go all the way back. So I want to find a Hamilton function. Again, that's not yet a quantum mechanical statement. I'm still in the world of classical physics. Hamilton wrote down his function in the 19th century. He did not have the benefit of Planck and Einstein and so forth, but he still did very valuable things with it. And there was also Lagrange, who wrote down a mechanics. And we use both, and in fact, it turns out to be convenient to get to a Lagrange function, to get to a Lagrangian for such a circuit. And I'll describe it in such a way that it will, in fact, work for any such circuit, any arbitrary Foster circuit. When I get to the multi-qubit case, the one which involves this rank 1 symmetric matrix, I need one more sort of idea of circuit theory, which will add a little bit more to the rules of the writing of the mechanics, of the Lagrange mechanics of these guys. Okay, now to write a Lagrangian, I'm supposed to assemble pieces of the energy and give them some label, which is that they're either kinetic or potential energies. And as you'll see, that turns out to be very straightforwardly doable in this setting if I choose the right variables to describe this circuit. Now, the kind of natural variables are the things I've been discussing over here, voltages and currents. They turn out to be not so convenient for writing down the mechanics, so we use their first integrals instead. Now, what do I mean by that? I zoom in on, say, one, what we call branch. So here's a network, an electric network, and this is an example of a branch. And a branch means, in graph theory language, an edge in the graph associated with this. So here's an example of a branch. And we can, like we did for the ports, discuss a branch. So, and there's some, again, it's a linear element, but this description will work also for nonlinear elements with some small modifications. So I will indeed begin with the thought that what I want to use as the state variables are voltage. So there's a voltage of the branch, and that means the voltage difference between here and here. Sometimes, or there is some bookkeeping, you have to decide what's the positive direction. And then there's a current of the branch, IB, and I will think of them in general as functions of time. Now, it turns out I want other state variables in order to get a Lagrange function in the right form for the elements that we have, these inductors and capacitors. And it turns out that this Josephson junction is, in fact, an inductor in disguise. It's a nonlinear version of an inductor in this setting. I will use instead the first integrals of these variables. Integrals. And what I mean by that are the following. So I construct a new object, which I have v of t prime dt prime, and I integrate from minus infinity to some current time t. So this integral is something that, well, can be given another time-dependent function, and it dimensionally has the units of flux. So I will indeed call it capital Phi for flux. And in my lecture yesterday, I immediately launched into saying, well, there's a flux field. But this is, well, you'll see in the next few lines what's the motivation for introducing it. I also have a similar integral for the current, IB. Now, this somewhat more naturally, dt prime, this has units of charge, so I'll call that Q, but it's a branch Q. When you start thinking about it, it doesn't make too much sense. It's not the charge here, it's not the charge on some node. It's sort of a counter that says how much charge has passed through this element. And similarly, in general, this is also a rather abstract object, this phi. It's just an integral of a voltage difference. However, for an inductor, it has a very direct meaning. Which is, let me jump so I can again follow in my own notes of exactly how I would like to say this. So, you can take it as a standard, statement of electrical theory that an inductor is by definition an object which has the following structure, that if, so inductor, symbolized this way, and it says that if there is, let's see, which direction do I want to say it? If there's a current, IB of t, then at that same instant in time, it produces a flux B of t, and the coefficient is it's a linear, relation between them with one physical constant, which is the inductance of that branch. So, I think you surely learned that even also again in college, that there's this object and this has units of Webers. And now I can do this thing of, how do I want to do it? Well, I can run this backwards, and then this, you recognize that this is the same as saying that this is L times dQB dt. Now, I can go on to the capacitor. It has a sort of similar looking object, but so you see, I've now written this in terms of the pair of variables, the phi and q, that I will want to use for this, calculation. Now, what am I trying to calculate? I'm trying to associate an energy with this branch, with this inductive branch. And the way I do that is I use, you might say a work hypothesis or something like that, but you may just take this as a fundamental observation of electric theory, that there is I'd rather do it on here. Let me just set this up so I see it here. So the fundamental fact that we will use a few times is that there's an energy which is again related to these currents. So there's a branch current times a voltage. So voltage times current has something to do with power, if you know about resistors, say. But in this setting, you say, okay, I do this and I integrate, I just keep track all the way from the beginning of time till now, dt prime. And that will be, by hypothesis, the energy. You can give arguments based, on mechanics.
Larger fault. When you write.
Larger what?
Larger.
Oh, I should write a little larger. Yeah, thank you. This is indeed an important equation. Okay, I won't further justify this, except to write it really big and to make, emphasize that it's a definitely important equation for this. Now, let's apply this. Maybe I can fit it in here, but I have to also write large. I can apply this in the case of the inductor. And the way I want to do this is to use this replacement. Which replacement do I want? Oh, I see. I really wanted to do something additional. I should have taken the first derivative of this, so that I can also do. So phi b dot, time derivative, is of course L times the IB, maybe I'll di dt. branch. Now this I recognize is indeed the voltage, VB of t. So that's actually the form in which I would like it. So the voltage is proportional to the instantaneous time derivative of the current. That's defining one of the several equivalent ways of defining an inductor with the coefficient, linear coefficient L. So I plug that in here. I'm going to plug this in. VB I plug in here. So let me let this derivation travel up here. Integral dt prime. Oh, and I should have kept, I did. This is not to infinity, it's to t, the current time. dt prime minus infinity to t. IB I leave alone, IB of t. And V I replace as shown. So I have an L, I'll put the L outside. I have di b of t dt. I have primes here though. Okay, now recognize this. This is one of these features of calculus. I can look at this combination. I see this is actually an integral over current. So it's equal to L times integral again, minus infinity to t, IB of t, dIB of t prime, but I'm changing the integration variable, so this integral should now be over IB, and I can get rid of these basically, and I have IB at the current time. This integral I can do, and that says it's equal to 1/2 L times IB squared. So that's one version of this derivation that, now what it shows is that the idea of the energy function is a good one in the sense that the energy is not a function of anything about the past history, it's just a function of the current state. And that's the, sort of essential, feature of this. Now I can do a replacement. I can go back to this equation and say, well, this is not the only way now that I can write this. I wrote it in the current form, but if I replace current by flux, I get another form, 1/2 phi b squared over L. And that will indeed be the important current or, energy expression that I will employ. And, I'll be indeed featuring that phi will be the coordinate variable of this mechanics. And so I've succeeded in deducing a contribution to the potential energy of the Lagrangian. And it says for each branch, I just go into my circuit. Every time I see an inductor, in this one I only see one at the moment, I say, energy check, and it's related to this branch variable in the way I've just shown. There is a kind of similar derivation, but maybe I will not go through the entire story, but it's very similar calculus. And I will deduce that the energy expression, now I'm going to go all the way over to here, will be by similar calculus deductions, but I will begin, it will be again, I use this fundamental IV formula. Where was it? Yes, the one I made large here. But now use the equations for the capacitor. I didn't write the equation for the capacitor, so I guess I'd better do that. For the capacitor, the hypothesis is, or the meaning of a capacitor, of a linear capacitor, is that the Q variable of the branch at time t equals the voltage of that branch at the same time t with a coefficient of proportionality c, so and so many farads. And then derivation will give us an energy expression, which it turns out I can also again write in terms of the phi of the branch, but the energy expression will be 1/2 1 over c phi b of t dot time derivative squared. You can kind of imagine why that would happen. But again, since I'm not doing the full semester version of this, I won't do this derivation. So I have an energy. Now I haven't yet called it anything. Except I guess I have it wrong. This is the C is upstairs. Sorry, excuse me. So this should be familiar to high school. That is, this you have to remember: 1/2 CV squared. Check. Now that's, if you ever learned any electric theory, including in high school, you would maybe learn that that's the energy stored in a capacitor, proportional to the voltage squared, which is the phi dot. But notice from the point of view of mechanics, so mechanics says that phi is like a coordinate, so it's like a position in some abstract space. So this says, this is an energy which says I have I have a potential energy proportional to x squared, position squared. And this is another contribution to the energy, which says that it's something proportional to, well, the velocity squared, dx dt squared. So this is 1/2 something velocity squared. So it should sound familiar, and this should sound like a mass. So if I have only one capacitor and one inductor, and that it would indeed be the circuit like this, that's why we say that this is a circuit exactly analogous to the dynamics, or describing the dynamics of a particle in a harmonic potential with mass C. Now, of course, the dimensions are wrong. C does not have the dimensions of mass because phi doesn't have the dimensions of position. However, if you felt like, you could do a rescaling if you wanted and introduce some dimensional constant. So this had the dimensions meters, or velocity meters per second, and then this would really have the dimensions of kilograms. Sometimes we do that, but it's not really necessary for this. Okay, now, and now the further steps are just to say, well, that's an energy, but we'll call it a kinetic, kinetic energy. So it's the kinetic energy associated with this branch. Now, there are a few other, further bookkeepings. That is, that branch variables are not all independent from one another. That is to say, if we have this branch, back to my transmon resonator circuit, if I have this branch and I've described things, and I have this branch and I've computed things, then this branch, so I'm talking about this branch, and then I've also accounted for this branch. This branch variable is not independent from those, because the phis satisfy a kind of Kirchhoff law. So the branch phi, just like for voltages, the voltage from here to here, plus the voltage from here to here, plus the voltage from here to here is 0. The voltages around loops are 0, and also the fluxes, branch fluxes around loops are also 0. There are exceptions if we worry about magnetic fluxes, but again, in the 1 week version of this, I leave this out. So one has to impose these as further constraints, and there's some graph theory for how to do this for more general networks. But I will not maybe develop this too far in this lecture, because I'd like to get to maybe some real physical insights. But I have a little bit more work to do still, because I have a kinetic and potential energy. Now, the Lagrangian theory says I should just subtract. In other words, kinetic minus potential energy is the whole Lagrangian. So Lagrangian so will be L will be sum over branches. Well, first the C branches, and I'll get the kinetic energy, T sub B of those branches. So it's a sum over B for branches, and then I have minus sum over L branches, B, and this UB. So that covers, well, almost this whole circuit, with the exception of constraints. That is, when I get to this branch, I shouldn't introduce it as an independent dynamical variable. I should just call it the difference between these two branches. So I get to, I study the circuit, and I can deduce that there will only be two independent variables which are associated with, in this circuit example, will be associated with this node and this node. And well, I have a node here which I tend to call ground, but in other words, all branch variables are constructed with reference to ground. So this minus ground is a branch variable for this branch. This minus ground, which you can call 0, is the branch variable for this. And then this minus this is the branch variable for here, which will involve this capacitor. Okay, so I hide these rules a little bit in writing it this way. Now, I crucially haven't said anything about this. Now, I will just introduce by hypothesis how this works. And I will state that it is something that behaves like an inductor. So it's something where, so the Josephson junction. I will go straight to the hypothesized energy function. So it will be a contributor to U. So if the branch is a Josephson branch, then this will be, as I said, by hypothesis, a function only of the coordinates. So it's a function only of phi b at time t. But it will, by contrast to the regular inductor, it will not be a quadratic function. But the physics theory of these say that it is in fact proportional to a sinusoidal function. So we write it the following: minus ej is something, just to give it the right units, cosine. And now it's a function of phi b, but it can't, I need to put something else in here because that's, well, I need to make this dimensionless, right? So cosine cannot be dimension, yeah.
A couple of questions. So those two circuits are equivalent, right? Those two circuits are equivalent. Right?
Yes, in the sense that you could, if you were told what the physicist thinks these three parameters are, they can be encapsulated in these two parameters, and a small change of the inductance.
Okay, so if I write the Lagrangian for that circuit, so the Lagrangian of that circuit would involve, right, yeah. So I would have...
it turns out the Lagrangians of these two circuits can be put into equivalence. So okay. Even though this it has one more branch, but it will have terms that can be absorbed into branches of this form.
So I would have three phase variables, right? There would be three phis.
Well, actually, maybe the clue is that if I do this node counting, that is, I have, how many nodes does this have as a branch? Well, it has a ground, and it still indeed only has two, or it has exactly two nodes. Okay. So it's structurally equivalent to this. It has the same dimensionality of the Lagrangian.
So then there are only two phis.
And indeed, this is in both cases, this is a dynamics in two dimensions, phase space 4-dimensional. And as I said, it turns out with choices of parameters that are in fact identical. So, and it's, well, as I said, the physicist prefers this because it's more descriptive. But the Foster theorist prefers this because it's a good canonical form. And in fact, you would say, if you write the Lagrangian for this, you simplify it, and you find these three capacitances don't appear independently. They appear in certain combinations. And that's the clue that's given by this, that this tells you what these combinations are. Now, these are quite relevant issues because the issue of how the capacitance finally appears in the Schrödinger equation. I mean, I'm getting step-by-step to quantization. I haven't yet introduced any quantization hypothesis. This is all classical mechanics or observations about classical mechanics. That will even be true when I finish this equation, and you'll see h bar. Okay, see, so it has to be quantum mechanics. Well, yes, sort of, but actually, at the moment, it will only appear as a scaling constant. Okay, so this can't be right, and it has to be something else. And of course, the Josephson phenomenon is quantum mechanical. So even, in its discussing what its classical consequences are, it's not maybe surprising that some quantum constants will come in. And it turns out they are the following. And I'll write it. There are several possible ways of writing it. So indeed, Planck's constant over 2e, excuse me, and a 2 pi here. Okay, so that's, notice I put a minus sign here, and it's useful to observe what is this at small phi b. So if phi b is small, then indeed it is harmonic. So it's a function like this, but continues on like so, rather than continuing like that. Now, the fact that it's a periodic variable of the phi then raises some, you might say, issues, because we write this, let me squeeze this, I shouldn't be squeezing, right? But Ej cos phi. The reason for just giving a different name is that it has other significance in the theory of superconductivity. This is unique to superconductivity. It needs superconducting metals. And this phi is actually an order parameter. So those of you, I mean, now solid state physics, phi is indeed the order parameter of the phase of the order parameter of the superconductor. And now you're told that this order parameter is a U1 phase, so that it should only be considered as a so-called compact variable, 0 to 2 pi. And sometimes that's further imposed, and it depends on the circuit whether it's clear whether it should be imposed or not. And in this circuit, it's imposable. That is, it is possible to insist that the dynamics is not in R2, not in a two-dimensional plane, but rather on a torus. That is, you would come to the thought that this variable is surely not compact. I mean, it has a harmonic potential, so it you can't cut it off at minus pi to pi. This one, at least, it's consistent with compactness. That is, that you only consider the domain from here to here as, and with the variable wraps back on itself. That turns out not to have too much effect on the modeling of the transmon. It has some, though, and it remains a bit controversial, actually, whether you should or should not accept this compactification hypothesis. If even that is independent of the quantization of this, I would point out that you're considering a dynamics that's either on a torus or either on a cylinder, I should say, or on R2. And it's both reasonable classical things to do. Actually, the classical dynamics will be completely equivalent. There are actually, however, differences once you get to the quantum dynamics. Okay, but this I won't spend much more time on, except to say that what we, quote, discovered recently is that this law is not quite true, and that, sorry, now I'm going to, I keep sneaking things in. People should object if I'm making things too small or chaotic or something, because now I'm going to say that I can't resist saying that what we recently discovered, I'll put a new discovery in some other color, is that actually for many Josephson junctions, the more correct law is this. So it's minus, and it's about 5% of Ej, and then it's cosine 2 phi. And it turns out the physical theory does not object to having such extra terms, such an extra harmonic in the characteristic of a Josephson junction. It requires some more story about, tunneling of pairs, two Cooper pairs at once and things like that. So a detailed condensed matter model will give it to you. But it wasn't previously known that the junctions that are actually used, I go back to the very beginning in the first picture, with this specific junction, fabrication method, that it would actually have extra terms, and they're not very big. But the point is that experiments were set up, and there's small experiments, one qubit and one resonator, just like these, and very careful studies of the physical behavior of these, and it was clear that it was necessary to add these terms. So that sort of illustrates the high precision aspect of this theory, that you can really take seriously small correction terms and really document that they're there. So in general, this is a whole Fourier series, but there are good reasons why it's very heavily dominated by the first term. So we'll stick with this as the hypothesis. Now that doesn't do anything very complex to the Lagrangian. In fact, I don't change it at all. It's just that when I come to an inductive branch, which happens to be a Josephson junction, I use this law for the potential function, potential energy function, rather than the quadratic one. And yes, Planck's constant has appeared. However, all of this is classical circuit theory, which just happens to have a funny scaling constant. This is the so-called superconducting flux quantum. That's the sort of the natural units that you must measure fluxes in. Now, I mean, but it's quite a peculiar flux in the sense that, unlike with these inductors, if you went in with a magnetometer while it was running and there was a current, you would actually measure a magnetic field near these inductors, and it would correspond to the amount of magnetic flux that's in these equations. However, if you put a magnetometer really close to the Josephson junction, you'll see nothing. So there actually isn't a flux. The branch flux does not manifest itself as a magnetic field, paradoxically. So it's sort of an internal energy. It's so-called kinetic inductance. So it shows that this idea of flux in the end gets to be quite formal here. It does not correspond to actual magnetic fields. Okay, now I have one sort of labor to inflict on you, but mostly it will happen the next time, is that I want to go from this to a Hamiltonian, because I do actually want to discuss the quantum dynamics in terms of Schrödinger equations. So I want to do that before I quantize. Now, okay, show of hands, you theorists out there, are you all comfortable with the Legendre transformation? Oh, great, great. Okay, so this is really promising. So I won't have to belabor the point extremely much, but I'll probably do a little bit more than simply wave my hands. So I have this Lagrangian, which is totally conventional Lagrangian. That is to say, particles with a mass with some potential. Now, okay, it's a bit of a funny mass. That is, each of these terms has a different coefficient in general. So each of these capacitors is different depending on the branch. I emphasize that there's some big ones, there's some small ones. And so, for example, in this two-dimensional problem, there will be not a simple scalar mass, but it will in fact be a sort of effective mass. And it'll have a different mass in one direction as the other. And it turns out this element says the mass is not even diagonal in the variables that I've chosen. So the principal axes of the effective mass tensor will not line up with the coordinate axes. Okay, well, why not? I mean, this happens in semiconductor physics. But it does lead to a bit of a complication. But I'll spend some time on this next time of why this is so. That the way you'll summarize this is, let's take this two-dimensional example. I'll have my variables phi 1 and phi 2. Now, I've been saying branches, but now at this point I can, very specifically say I have a phi here, and then what I mean by the branch flux is this minus whatever it is here, which is 0, and then I have phi 2, and that will suffice for these two branches, and then when I have a branch like here, it'll involve the variable phi 1 minus phi 2. And that's why this capacitance matrix will be non-diagonal. So I'll just call it C11, C12, C21, C22. And I can complete this by saying this equals phi 1, phi 2. So this is a good sort of matrix vector way of writing it as explicit 2x2 matrices. Now, it turns out that when you have these effective masses and you want to get the Hamiltonian, you have the chore, which is sort of bothersome at times and actually really troublesome for these networks, is you have to invert. Remember, your basic kinetic energy that you have, you on the one hand write it as 1/2 mv squared, dx dt squared, or you write it as p squared over 2m. So there's the inversion. Mass goes downstairs when you write things in terms of the canonical momentum. For us, the canonical momentum is this charge operator, which I've otherwise been neglecting, but it comes back when you do the Legendre transformation. And you have to invert, and it's not a simple scalar inversion. You have to invert this as a matrix. It has the annoying feature that if you have a network with, I want to go back to this, your network with very local capacitances. I mean, here I can point, you can't see it at this magnification, but this is actually a kind of discrete capacitance. So yes, it's a capacitor. It only involves this node variable and this node variable, you might say. But unfortunately, like banded capacitances, if you invert, is not banded anymore. And so you can end up with effective interactions. This inverse mass can be kind of all over the place. And it is a problem with maintaining the sort of locality of description of these multi-qubit structures. Just the fact that you need to invert capacitance, and it is inverted as a matrix, to get the kinetic energy in the Hamiltonian language. Okay, but I'll come back to that next time, and now I have 48 hours or 46.5 hours to think of what I'll say next time. And I have so many things to say, but I'll find a good selection of things. I will, without question, I will complete my analysis of the transmon circuit, because you want to be able to see, yes, we get the usual qubit resonator coupling, the Jaynes-Cummings coupling, that you could, with a little bit of addition, you can make a measurement setup, very analogous to the Haroche setup that you heard about yesterday. But I definitely want to say some further things about multi-qubit structures and about some of the paradoxes of what you run into, or the additional structure that you need once you go, it's been erased already, when you go from one port, which I've reverted here, to many ports. There's one crucial structural change, which is transformers. And I'll explain why that actually comes up and is sort of unavoidable, unless you like negative capacitances. But I'll explain why those are two sort of unpalatable choices which you have to deal with. You can deal with successfully, but I think for today that's enough. Okay.
So, thank you. Do you have some question or something like this? No comments or questions? Yes?
Microphones?
Yeah, it works.
Yeah, it's a kernel with a 1 second delay.
Yeah. Hi. Yeah. So thank you very much for this talk, David. Could I just ask a small question, which is, if you have linear constraints, typically in mechanical systems, so if I have some sort of classical mechanics problem with a linear constraint, then I would add it with a Lagrange multiplier to the Lagrangian, and then use the derive the adjoint Euler-Lagrange equations and use them to eliminate and push it back. This is standard technique, right? What did you do to Kirchhoff's laws? I really missed this point.
Yeah, we found that it's sufficient to kind of impose constraints by hand, and I sort of did that here. That is, I started with a circuit with, multiple branches. I have 1, 2, 3, 4, 5 branches. And so according to the way I initially said it, I would have had 5 variables, but surely that's wrong. Yes. And I've explained, so Kirchhoff's laws say that there are linear constraints among these branch variables. So I'm invoking the Kirchhoff law that the voltage around a loop is 0.
Yes, yes.
And that's enough to get rid of, and also the fact that you only need differences of branch variables. That's enough to take 5 down to 2. But I don't need to use Lagrange multipliers to do that. I do that algebraically. That is, I just can see that the 5 variables are writable in terms of the 2, and I just go ahead and do that. Yeah. But that can be done in a very well-organized way with graph theory and writing trees of the networks and things like that. Turns out transformers will add yet another layer of constraints, but which again can be imposed sort of by hand.
So you don't ever need formally to use the this technique of using kind of this adding the Lagrange multiplier?
We have never had a case where Lagrange multipliers were a valuable approach. But it's within this context. I don't disparage Lagrange multipliers overall.
Sure. Thank you.
So see you on Thursday.